Okay, hello everyone. So thank you for joining for today. Before we start, I want to remind you that please fill in the survey. You can check the survey on Google Classroom or the Moodle, the last posting. You can check it out. So by this end of the hopefully this Friday. Okay, so Friday I will announce the schedule for our final. So I hope everyone fill in the survey and let me know what other schedule you have, so that I can pick one schedule that available for everyone. Okay. Okay, for I want to have some exercise first, maybe 2 or 3 questions, and then we can move on to the next section of in our chapters. So we actually have discussed until the 15.2, 15.3, the polar, and then 15.5, the surface area. Okay, and remember that we are skipping all this 15.4. Okay, now let me give you an example. Okay, evaluate this double integral with D is region of triangular region with vertices Okay, let's try this one. Maybe I'm giving you 2 questions. Wait. And then the other one, this is number 1. Number 2 is evaluate Okay, let's start from the first one. Maybe I'm giving you 5 minutes to check. Okay, so you can start to calculate what is the multiple integrals for number 1 and number 2. Okay, so let me give you 5 minutes to try, and hopefully you can evaluate these two integrals. Okay, so for number one, is there anyone who will finish? Anyone finish number one? Evaluate the double integral. You can write in the chat box if you finish. So let me draw for you here. Okay, let me just draw the region. It's on between this point and let's say this this point, and also this point here. Oh, okay. Okay, we have the triangle on the region. So this is the region D. Okay. So this is the region D. Okay, now what can we do now? So first, I think it's by using the same perspective on the calculus one that you have learned before. If you see this kind of shape, the first thing that you can come up is that you will take the x or the y. So here the my suggestion, if whenever you find this kind of questions that you can somewhat create the order for the integrations, you can take x as your constant or y as your constant. Okay. So if you have this kind of shape, which one you are going to use, x or y? If you choose x, this is what will happen. So you need to take this until here, right? And you have these two y as your equations, and you need to also have the second region here, right? So this is the first, this is the second, in which you need to combine both of them. And of course, it will be taking your times, right? Instead, why don't we are using the y? So if we take y as our constant, we can look from 0 to 1 here. So from 0 to 1, so it's from here to here. That will be our constant. And then the x will be this line here minus this, right? Okay. So this will be better if we want to have, so double integral, and then take 0, 1, that's y. And then we take, so let's naming all these lines. So this line is, it's the same x and y, so it will be y equal x. Okay, and what is this part here? We need to make some line equations there, which is, we can take these equations. The gradient is y, right? Is 1 over 3. But because it's going down, it will be minus, right? It will be minus, right? And y1 is 0. Let's take this 4 and 0 here. And this will be x minus 4. So this is our line. Or in terms of x, we have 4 minus 3y. Okay. And basically this x equation here will be minus with this one. So I will write into our equations here that this is 4 minus 3y minus y there. So this is x, this is x, this is y. And then we are put our y and then the x dy, the multiple integrals. So we can integral this easily. So we can integral with respect to x. So we take that. And we will have 4 minus 4y multiplied by y. And it will be so it's half minus 1 over 3. So it should be 4 over 6 or 2 over 3. That's how you got the answer. Okay. Any questions from the first one? Any questions? Okay. The second one, evaluate this integral. If there's nothing, if there's no information about how to do the integrations, what you can do is first look at the equations. Okay. Look at this y here, right? And when you are dealing with these integrations, because we need to integrate the inside first, if you think that it will be a trouble when you're dealing with these integrations, we can always change the order. Okay, we can always change the order. So first, we can try to look at what we have here. So the first is x, right? This outside integral, x equal y, x equals 0, and this will be y equal 2, y equal square root of x. So when we try to reverse, becomes the x dy, we need to understand what kind of equations we are dealing with. Okay. So first you have the here. Sorry. I think I have take it wrong equation. Sorry. Should be 4. Okay. Okay, so first is taking this into y squared like that. So we will have a quadratic y squared. Okay. And taking into y equal 2, and take it to okay, that's y equal 4. Sorry, I have make mistake for the equations. So this will be the region. Okay, so if we want to make the order to become x dy, then this will be y equal 2, x equal 4, right? So we need to look at the y is from 0 to 2. So first we can write 0, 2. And then the x will be from 0 to y squared, okay? 0 and y squared. And then we can start to write the entire equations, and this is our equations now. And check can we integrate this? I think we can. So we can integrate that and becoming x and then y cubed. And we can just plug in and you can use these substitutions. Let's substitute this. Okay. So we will have 1 over 3 and then 1 over u, right? And 1 over u, we integrate, you will be ln, right? Ln u. So you will have 1 over 3 ln, and then u is y cubed plus 1, and then 0 to 2. Or we will have 1 over 3 ln 9, right? This will be the answer. Okay, I hope you get this. There's two questions, which is the first one is to define the which part that you want to integrate. Okay, which one is the constant, which one will be the variables, and the second one is to deal with when you want to reverse the order. And essentially, reversing the order means you need to look at how the equations look like in the graph. Okay, we can move to, I think, the last part that I told you is the surface area. So the next section after the surface area is the triple integrals. Okay, so all of this is the double integral that you already learned. And now we will move on to the triple integrals. Or this is the 15.6. Okay, from before, so previously, in double integral, you have the surface, right? And you are mapping this to the region here, right? And basically, you are evaluating this as volume, right? Volume. And you will have a small rectangle here, and you can define this as delta x and or delta y and delta x, right? Now, if we are looking at the triple, what does it mean? Let me take some. I think this, yeah. If you look at the triple, okay, what you're looking here is basically, imagine there is a building blocks, okay, and then you can see that in the picture the building blocks was cut into pieces, okay, and basically in triple integrals what we are going to observe is this little, let me make a red one, this box here. And if we're looking at this box, we will have three components, okay, delta y, delta x, and delta z. Okay, so if we have a solid in our xyz plane, then we can also approach these blocks with Riemann sum. Okay, but let me write what we are doing here first. So let's say we have a closed solid. Let's say solid B, right? It's contained in a box. So the idea is divide B into sub-box. That's small boxes, right? And then volume of each sub-box, right, is delta V. And the coordinate and the point is now you have I, J, and K because we are dealing with three axes. And the triple integral then or maybe of f over the box B is so B. So the difference with, from the previous double integral, the region now is 3 dimensions. Okay, the region is 3 dimensions. Okay? So B region is now 3D. Okay. So the integral, and we are using dv now. Okay, is equal limit. Now we have L, M, and N. We have 3 components instead of 2 in double integral. So we have 3 sigma. L, M, N. And then F. And then delta V. So this Riemann sum is our definitions of limit integral. And it has also same property with the double integral, which is the same theorem that we can apply. That is the Fubini theorem. So whenever you find the region it's having like x or cross like this, it means that it has x, y, z. Okay, so it's multiplications of the base and the height. Okay, so we can put in our AB, CD, and RS as our boundary. And let's start with dx, dy, and dz. So dx is A, B, C, D, and R, S. And you can basically changing the order. So you can have dy, dx, dz, or dz, dy, dx, and various order. Okay, at least you will have 5 other, right? Okay. I believe the way you integrate, it's similar to double integral. The interesting part is when you are having triple integrals over general regions. Okay, we can look on that sections after this. Okay, any questions? Okay, now we can look for the next sections. The next section is the general regions. So triple integrals over general regions. Okay, yeah, let's draw the space. Now, the bounded region, as we are mentioning before, it will be a solid. Okay, it will be a solid. Let's say we have in your, let me check. Okay, so let's say we have the E. Let's say we have E as our solids, and these solids will be projecting through xy plane, and it will be resulting another region we call D. Okay. Okay, what's interesting here, in double integral, you are having the surface, right? Only one layer. But now you are having two surfaces, okay? Two surfaces that make up the E. So for example, this we call Z. Let's say U2, it has double integral. And now you have U1 for the lower part. So I hope you get the idea behind this triple integral. So in double integral, you have only one layer, and then you can see what is happening on the region D, right? So here, what is really happening is, imagine that you have only one layer. Okay. Imagine you have only one layer, for example, only one layer here, and then you have D here. Imagine that when this happens, your integration is double integral. You have D, and then this is fxy at dA, right? Okay. Now, we make this as solid E here. And what will happen? What will happen is you still have D, but you have another integral that sets up the U1 and U2. And this will be XYZ. And this become DZ, DA. Okay, get it? How the patterns will be. Okay. And it's not always XY, it can be YZ, it can be XZ. And the way you are looking at the D will be also different. It's not always on the XY plane, it can be in another plane. But let's say the default, our default system to make you easy to understand the triple integral, let's make all D on XY first. Okay. And I will make all the question in the XY first. But it will be the same if you are going to change the D and the E. Okay. So we can say that the integrations or the triple integral with region E okay. So the pattern, okay, in triple integrals, remember that in double integrals, you have a constant like a, b, right? For example, if this is dy dx, so this will be x as a constant, and this will be y. Maybe you have, for example, like equations, or maybe let's make in f f1x. This is f2x, right? And maybe this is the surface that you can have. Okay. So this is a constant, single variable, and then the second part is you have, if you are having triple integral, you will have, this will be dz, and this will be, let's say, uxy. Okay. Okay, so let me write some summary. So first, when you're dealing with triple integrals, first you need to find upper and lower boundary, surface boundary. Okay, surface boundary of solid E. Okay, so this is solid E. So you need to find this first. You need to define this surface. Okay, and then take or make sketch for D. Okay, the projections. So take the sketch for D here. it's the same thing as the double integral. So, and then treat like double integral. Okay. So like I said before, if you have, wait, let me draw. Maybe, okay, maybe you have here, this is the E. And this will be, what is this? This is the, yeah, YZ. So you will have, this is, let's say V, YZ, V, V2, V1, right? And you need to project this to the region on YZ plane here. So this is E, this is D. Okay. So you need to make sure that you know how to read, okay, how to read the equations given. And you can take them into sketching. At least what you need to sketch is the D. Okay, this is the important one, because sometimes when you have the surface here, sometimes you cannot really sketch the surface because it's a little bit too complicated. But as long as you know which one is surface one, which one is the surface two, I think that that should be enough. Okay, should be good enough. Okay. So actually, based on your textbook is actually making some sections in itself and in the same chapter, in the same sections. But I think as long as you know the idea, for example, here, the first one here, the picture, the D is more or less, it's not really give you any information, what kind of equation it has, right? So you kind of not really sure what is going on. You need more information. If you see the other picture right here, it's the same xy here. Z is a function of xy, but in D, you will see that it has y is function of x. So you kind of get the information what you are going to do, right? So here you can take the x as a constant. So the idea should be, this should be dz, dy, dx, right? Okay, got it? Hope you get why I'm treating this as dz, dy, dx. Because you know from the d, you get the function of x for y. So y should be not as a constant, right? Instead, the constant should be x here, a, b. So a, b, and then this will be g1x and g2x. And the last is u1xy. Okay. And also the same if you have function of y. If you have function of y, then it will be dx dy. Then y will be a constant, right? Okay, so if you think, if you separate, become like making type 1, type 2, type 1, type 2, like this, type 1, type 1, and then the projection is type 1, or maybe type 2. So type 1 projections, type 2 projection, or type 1 solid, maybe type 2 solid. So let me see. So solid, it will have type 1. There will be 3, right? Because 3 variables or 3 possibility. So first is like the first one that I draw. This is the projection here. And the second, probably the YZ is maybe here. And we have in YZ plane. And the last is here. But it doesn't really matter if you don't know which type you are on. Like what is type 1, what is type 2, what is type 3, it's not important. The important thing is when you have the exact information of the functions, you know how to put the functions. Okay? That's the most important. Like for example, like I told you before here, like when you have this kind of information, oh, you know the z is xy, and y is function of x, so it should be dz, dy, dx. You don't really need to be like, what is this? Is it type 1? Is it type 2? Is it what is the projection will be? That's not important. Okay, I hope you get my point. Okay? I hope you get my point. So type 1, type 2, type 3 doesn't really matter. Okay, what really matters is when you have the questions, when you have the given information of the exact equation, you know how to treat the equations into your triple integrals. That's the most important thing. Okay, let me give you maybe some example. Okay. Okay, let me write the example. Okay, let me write triple integrals and then t z dv. Where the t is tetrahedron bounded by n plane x plus y plus z equal 1. Okay, because I think tetrahedron is not too difficult to draw, so we should try to draw that one as well. So let's say this z, x, and then y. So the plane first, x, y, and z. You can try to check. And because you have z equals 0, y equals 0, and x equals 0, that is also the boundary. You can check that out. So you have, if you draw, let's say this is 1 here. Okay, that will be our tetrahedron. And this is 0. So we have like a triangle with four triangles, right? And that makes volume. This is T, right? The volume T. Now what will going to happen is first we need to decide which one is our integrations. So first, look at our boundary here. So basically, you can take a look here. You can take the projections to XY plane, to YZ plane, or XZ plane. Doesn't really matter. It should be the same because you are exactly looking at the same perfect solid, right? You can do the projection in three ways. But let me do it this way. Let me make this into Z is 1 minus X minus Y. This is the surface for Z. Okay, so I believe we can also make this. If you want to make dz at the first, as the first step for integrations, the inside integration, you can start from 0 because all will be, it's bounded to 0, right? All is bounded to 0, and it will be 1 minus right, minus X minus Y. So that's for dz. Actually, you can start from dy, dx, dz because all is related to this plane equation, and you can switch x, y as you want, as long as you are correct. Okay. And the second, let's make dy or dx. So first, if we look at these equations and look at the boundary having all 0, so we can try to make first, let's try to make y 0. And we will have, or maybe because z already been used, let's just using the z instead. So we will have x plus y equal 1, or y is 1 minus x. So let's start y. Okay, let's start y. So dy, it starts from 0 to 1 minus x. And then dx is the constant, 0 to 1. This is 1, 1, 1. So first you are looking at the surface, okay, and you can project to this xz or yz or even the xy. It's up to you. But in my case here, I am projecting to xy plane. So I'm projecting to here. And then you can look at from x equals 0 to x equal 1. And this will be the y here. So this will be the y minus x. Okay, I hope you get the idea for this example. And I believe you can solve this, right? You can solve this first, and then later is the second one, and then last you can plug in the constant. I leave this to your part, okay? Okay, now let's see. Let me check. Okay. Okay, let me try the other example. Because I think the key for multiple integrals is having getting used to the first is the calculation itself, and the second one is to make sure that you understand the questions. What you need to find. First, you need to find the boundary. You need to at least sketch the projections, sketch the double integral, right? And then the triple integral is actually you're just adding one more layer to the integrations in which it is the functions of two variables. Okay, now let's try the other example. Let's try this is the E region, and then you have triple integral of x squared plus c squared, and this will be dv. And E is bounded by this is 4 to separate from y. Okay, so we have now now the giveaway here is you see this is x and z. So of course you will see this will be at least having function of x, oh no, xy, xz, sorry, right? And this will be probably, it can be z equal x, and this will be x will be a constant, right? But let's see what we are having here. So first, you can start to projecting to maybe the plane. Okay, because I think we can set up the graph. Okay, now we have the boundary is x squared plus z squared. So maybe drawing here, here, maybe using blue. And then y is equal 4, probably be here. So y equal 4 is there. And if we are including into the equations here, this will be the equations. So you will have the radius is 2, right? So this will be 2, 2. So at least if we draw the circle, that will be our circle. Okay. And then the trace is parabola from here. If you remember, it's y equal x squared and y equals z squared, right? So let me draw using different color. So, and then y and z will be maybe here. And then y and x, let me use different color. Maybe here. Okay, let me make it to clearer. Like that. Okay, maybe that is our parabola or paraboloid. And this is another circle that is should be the same as the color here. So maybe make this one bigger. Okay, let's say this is the circle. Should be the same. Okay. Okay, I hope you get the idea. So this is the paraboloid that we already draw. So you have the x squared plus z squared, the paraboloid, and y equal 4, which is here. Okay, first, let's say we have, let's say this is our d, the double integral. Okay, so we will have 2. This is -2, or maybe this 2, -2 here. This is also the same. So if we want to make triple integral, so first is this is the equation. So first, if we are having this is, let's say, x squared plus z squared equal 4, and you will have, okay, or maybe I will move here. So if you have d is this surface here, okay, that is our surface here, then we can take this into at least 2 equations that you can pick up as your choice for the boundary. You can pick up the z equal function of x or x equal function of z. Okay. Okay, let me write here is dy, dz, and dx. And then let's start from the outside is x is -2. And z. So z equal x, right? Z equal x here. So this will be minus. And then the functions of y will be here, function of y, because we already have these definitions here, and I think this is quite important to see. So whenever you have like this, you have already 3 variables here. Y equals x squared plus z squared because of it's x squared and z squared. It's better to have this, or maybe fxy. This will be the inside integrations. This is better because it's already having x squared and z squared. Instead of you are making another, like for example, y minus z squared and then plus minus, it's horrible, right? So it's better to have xz a function. So if you look from the picture here, for the y-axis, it starts from these equations, right? The paraboloid equations until y equals 4, right? So I start from this boundary until 4, like that. So we can start to integrate this. Okay, so it seems scary, right? But let's try to check the inside integration at least. Okay, at least check the inside integrations. Okay, so this will be 4 minus minus. Okay, let's check the inside. It will be just this, just y and then x squared plus z squared, right? And then plug in the x squared plus z squared and then 4. Okay, let's write that. So 4 minus x squared plus z squared, and then square root of x squared plus z squared. And we still have dz dx. Okay, if you want to try, you can try to integrate this, but I don't want to. Instead, okay, remember, we can also convert to r theta or polar. Okay, so in trivial integral, you can also convert the double integral to polar. So you can convert the all here into polar. So we can convert to, let's define the x squared plus z squared is our r squared. Okay, and all will be based on the polar here. So we will have this circle, okay, the whole circle. So the theta will be from 0 to 2 pi, and the r will be from 0 to 2, right? Because it's the maximum is 4, right? The r squared is 4, so r will be 2 plus minus 2. Or in polar, it should be all positive. So this is the best way to tackle this questions. So 0, 2 pi, and then 0, 2, and then 4 minus r squared. And then the square root is r squared, and then it will be r. And don't forget to multiply with r dr d theta. Okay, we will have 4 minus r with power of 4. Wait, wrong. It's better to look at here. So you will have r squared. So you will have 4r squared minus r with the power of 4. I think that will be better. So you can 2 pi 4, 3. Yeah, you can check this and calculate. Okay. That's the other example. Okay, any questions? Okay. Let me give you some additional notes. Or maybe just an example, and then I will give you notes. So express these integrations. So express in dx, dz, dy, and dy, dx, dz from these integrations. This is quite interesting. So first, to help you to imagine, let's try to draw. Okay. If we can draw, let's draw. I think we can draw because it's not too complicated. Okay, let's. This is x equals 0 and x equals 1, and then y equals 0 and y equals x squared. So we will have a quadratic on xy plane. Okay, so let me draw the quadratic. Okay, maybe that is our quadratic. This is y equals x squared. And this is x equals 1, although the proportion is a little bit wrong, but I think it's the correct. Yeah. X equals 1 there, x equals 0 here, 0 or origin there, and then z equal y. Okay, now this is interesting. So z equal y. So z equals 0 to z equal y. So maybe let's make the z equal y is there, and then imagine it's cutting all the way through the x-axis. So you will have, or maybe let me make that, and I'm making the real z here. And it will cutting the okay. And then you will have so you have this. Okay, I hope you get how to draw that. Okay. It's kind of, if you're not familiar, you can try to draw this as well. Okay. So the idea is first define all the uh, the boundary, right? And then try to combine all the boundary. So for example, you have this z equal y. So imagine z equal y is a line, but then you need to treat that line as a plane that cut out all the sections. So this is actually z equal y here, but it will be a plane that you can see that it will cut out all the x-axis. It's cutting here, right? And then you see that we have y equal x squared, like down there in an xy plane. But since we have z equal y here, and we also need to connect, okay, from this to this. How to connect them? We go up and we make this. So we make this and this. Okay. Okay. Now we have draw the, let's say this is the E region. Okay. Okay, if we want to have a projection to take a good look on how our solids will be in their respective projections. Let's do that. So let's see from the xy plane. Okay, so from xy plane, we only have the x equal 1 and y equal x squared, right? So we will have, let's say this is x equal 1. And then we have, this is y equal x squared. Okay, so this will be, let's say d1. Okay. Okay, the second one is, let's see z and x. So what will happen is you can rotate uh, the picture to the, so rotate there. So you will see this line will be like that. Okay, and this is precisely because because z equal y and y equal x squared. So z should be also equal to x squared. So this is what we have also. We have another functions that are not mentioning in the boundary, but you can figure that out, okay, from this equation. So you can conclude that z equal x squared. So you will have another parabola here. And let's say this is another d. And let's try to z and y. Z and y, you can look here and see it's just a triangle, right? A triangle from the z equal y. and we have y equal 1 here. And let's say this is D3. Okay, we can describe E describe, let's say we have the y is from 0 to 1. And then z is from 0 to y. And then lastly, x is square root of y to 1. Okay. And thus, we can have dx, dz, dy. This is from 0, 1, 0, y, and then square root of y and 1. Okay. So first is how to make the order is you need to take the projections first and then set up. So first is why I'm taking y as a constant, because I want to make the fit into the question here. The question set up, the last one should be y. So y should be a constant. But the second one, it's z. So we need to take z as a constant. So z as a constant, if you look here, you will get all the notions that having with z, it's having equally 1, right? Either y or x, they both will equal with z equal 1. But later, the second is dx. So we need to take with dx. Okay, we can write down the e. So first is z is from 0 to 1. And then we need to take the x, right? We need to take the x. X is, this is z. This is x. So z is square root of, x is square root of, x is, I think this should be, z equal x squared. Sorry. So we have x and then square root of z. So x is square root of z. So x is start from square root of z until 1, right? Until 1. So square root of z less than x less than 1. And then lastly, the y. Now y is from z to x squared. So it should be from this, from z equal y until the x squared. So this z equal y here, and then this is the x squared. So 0, 1 square root of c1, and then z, and then x squared. Yeah. And then functions of 3 variables, and then dy, dx, dz. Okay, there is actually a sections about the application of triple integrals, but I think that will be similar with what we have done. So basically, we are going to approach volume for triple integrals. We will going to review all of this maybe later, maybe next week we can review. But maybe before that, is there any questions? Any questions? No. So maybe in a very quickly, I will tell you that the idea is always having, okay, so you have triple integral, okay, so this will be a constant. This will be a single variable of functions. So let's say of x, or maybe y, or maybe z, okay, and this will be 2 variables. Well, it can be one variable, but you need to include x and y, or z and y. Like if you have like this case here, like this case here, you have y, right? But you need to include also z and x squared based on from your equation here. So you have z equal y and y equal x squared, right? So that way, you can see that even though it's not really clear from the drawing, but you will see that this is the very first part of z equal y. And then imagine it's going through here, and the next equation you have is this part, in which this is the y equal x squared. Okay, and that's why you are choosing the dy here, having from z to x squared. Okay. And we will skip all the so in the triple integrals, they are also about the moment, center mass, the inertia, right? We will skip this. So skip. Okay, and then let me move to a little bit introduction, if you wouldn't mind. Of course, I will review all of this and maybe give you another exercise a bit later to help you to solving some problems in your exercise. But let me introduce you into another section. Okay, another sections is called triple integrals and cylindrical coordinates. Okay, as a reminder, let me write the polar conversion uh, from the rectangular coordinate. Okay, if you have the theta, you have the r, and at this point, it's the same point in which you have the conversion happening between r, theta, and xy. Now, what I want to introduce you is another way to look at the polar, but in 3 dimensions. Maybe that is what we are going through these sections. So this Z, X, and Y. So of course you learn that here you will have the radius. You also learn that this will be the theta. Okay, but here in 3 dimension, we have uh, another variable or another axis Z. Let's say Z here. This is C. And the point here will be R, theta, as in the polar, and also Z. So we are adding Z. Okay, so we have X is R cos theta, Y is R sine theta, and Z is still Z. We call them cylindrical coordinates. Okay, why cylindrical? If you remember the quadric surface, whenever you have a circle equations and you have another axis like Z, you will have a cylinder-like shape, right? So for example, if you have like this is the circle, right? But you have also the cylinder like that. So we may also try to convert from x, y, z to r, theta, and z. So if if for example you have the surface z equal r, because we know that r squared is x squared plus y squared, right? And r will be square root of this plus minus. So z will be, or z squared will be x squared plus y squared. And it will be a cone, right? If you remember the quadric surface, okay? So I hope by using this conversion, you can at least convert the xyz to r theta z, and you can also describe some surface. Let's, for example, this z equal r, or maybe another examples as well. Yeah, but I think this is just the intro that you will have a new setup of system. Okay, it's called the cylindrical coordinates, in which you are having r, theta, and z. And maybe on Wednesday, I will tell you that in polar you have r dr d theta, and because now you have dz, so you need to add dz. So this will be the area, this will be the height, and that will be the volume, right? The volume of the cylinder. Okay, so I will leave that on to the next Wednesday. So, okay, thank you again for attending this class today. Actually, today is a holiday, so happy Dragon Boat Festival. Although there is no Dragon Boat now, all people working from home, right? So yeah, and don't forget you have exercise to check in the Google Classroom. And if you look at the number of the questions, I think some students take take it into the new textbook, the one that we are using, the 9 editions. But actually, I'm writing on exactly on the instructions that you need to refer the numbers to the attached PDF. So you need to use that PDF to check. Okay, so maybe if you have like friends that asking which number you are in, don't forget to tell them that you need to check the PDF because the number is different from the 9 edition and the other editions. I'm using on the PDF, it's not 9 editions. So you need to check the PDF. Okay. Okay, I think that's all for today. So you can leave the Google Meet, or if you